Okay, hello everyone. This is Shu Han. I'm a current PhD student at the University of Cincinnati, Civil Engineering Department. I'm working with Dr. Ma Jiaqi and Dr. Ming and Cincinnati Insurance Company to working on this roof risk image recognition model, and I will be giving a little brief introduction of how a computer can recognize image and how everything works. Okay. Um, okay. First off, what is image recognition? I think uh, this is a broad topic. So the bottom line is um, image recognition is basically using computer to recognize image or video because essentially video is just a whole bunch of image feeding into the computer in a really fast fashion. So they're basically the same thing. We can see there are plenty of examples that I provided. Um, there are computer recognizing human faces. There are computer recognizing landmarks, statues, lamps, passengers, and there are also a good variety of usage of this type of technology in a medical research area. On the bottom, there's a CT scan picture, and this is a medical model recognizing the liver and spine from a CT image. So basically, it's just pretty straightforward as the name suggested. An image recognition is essentially use computer algorithm to recognize features or items that we wanted from an image. Okay, now how can we do that and why is it a challenge for computer? So as a human, we automatically sees an object. But what we do is we see a bunch of features and then we recognize, okay, we combine all the features, combine the triangle ears, like here shown in the left, there's a dog. We see all those little features like curly tails is covered in fur, there are four paws, and then we combine them together, we see, okay, that's a dog. But for computers, what computer sees is just a whole bunch of numbers. I think as a dev students, you guys are really familiar with RGB system. Essentially, that's basically because the color are made out of computer color. Artificial colors are made of three basic colors: red, green, and blue. And computer uses the system to represent all different colors. Um, so basically, every color recorded in this format will have three layers, and each layer is a matrix. The matrix is just a whole bunch of numbers linked together, and each number representing the intensity of this color in that pixel area. Um, so, like I show on the right, what the computer sees is it doesn't see a dog, it doesn't see grass. It's just an image with three channels, three layers, and each layer has that many pixels with that many intensities. Okay, however, um, we found out that if we human can recognize a feature from a picture, then um, there's some relationship lies in those numbers that we can recover. We can find out to be able to distinguish different features, and that's exactly what we're doing with image recognition. Okay, so now let's go to the detail of how computer recognize image. So just like we mentioned, we human actually sees different features from an image. We want to be able to do that with algorithms. So we use a computation method called convolution, And this really is the building brick for all image recognition classification algorithms. This is the most basic item that we need. So a convolution is basically um, a function that, well, not a function. It's a computation method that gives the computer the ability to extract features from the image. And then once we have a way to tell the computer to recognize all those features, we also need to combine all the features because if a computer can see a bunch of furs, tails, paws, and ears, if it does not combine it, it will never be able to see if it's a dog or fox or cat. We have to combine features in different levels and essentially forms an object to be the input of the whole model so the model can tell that it's an actual thing that it's seeing. It's not a tail that it's seeing. So we use neural network to do that. Neural network is another hot topic. There are all kinds of different application of deep neural network. Um, Depends on different goals. The network may vary differently, but since we're talking about image recognition, we will be focusing on convolutional neural network. Um, so that's basically what we've been saying. The first part is a convolution. The second part is a neural network. And last but not least, the third goal is the label, because just as a human, a computer cannot learn without without a correct ground truth knowledge. We have to tell the computer that this is a dog, so that when something similar occurs, it can recognize it. Oh, it's really similar, and it's a dog. If we never tell the computer that what it is, it might just, well, it don't know what it is. There's we have to learn from something, and we're trying to give the computer the ability to extract the features, to combine the features, and we want the computer to learn from us. We tell it what it was, and then when something similar occurs, the computer can see it. So let's start with the goal one, which is the convolution. So this is a bit tedious. I try to be not technical as possible, so that you guys can understand what's actually going on. It's actually really simple, as a matter of fact. So the convolution, as mentioned earlier, is an operation between two functions. It's written as f star g. Well, if that's not relevant if you're trying to write a paper or anything, so I'm just putting that out there. The formal definition is the convolution is the integral of the product of the two functions. What that really means is we take values or numbers from two different functions. We first multiply them and then add them all together. That's it. That's the convolution. Uh, we take two numbers from two functions. We first multiply it and then add them all together, and that's all that matters. It's just basic convolution. It's just simply what it is. And then the main takeaways I want you guys to know is the convolution is an operation that enables the computer to extract different features. And this is the building block for image recognition. Without convolution, there's no way the computer can recognize features, and without features, there's no way that the computer can ever recognize anything from an image. So, how convolution works, how does it extract features? I will give a really simple example here. It may look intimidating, but let's go through this carefully and slowly. It's really simple. Um, so this example is edge detection. So edge is basically the edge. When I see deaf students draw a lot of drawings and you curse uh, not curves, trace from different pictures or drawings. So basically, an edge is what you're looking for when you trace from another picture. And this is a really fundamental feature that the computer needs to look at when it's extracting features. We Well, that's obvious because we need to detect all the edges to be able to find the item that we're looking at in the picture. Okay, as we mentioned earlier, each image are represented as three-layer matrix, three-layer numbers RGB. They are they're stored as a three-layer matrix in the computer, and each number in that matrix representing the intensity of that pixel. And then by analyzing those numbers, we can find the relationship. We can find some weird quirks and features of that numbers, and then we can say, okay, if that happens, then that's the feature. So for edge detection, this is a really obvious example. When there's an edge, there has to be a dramatically different intensity between two sides of the edges. So as the example shown here, I circled the chin of this little animal. I generally don't know what it is. I just kind of found it on the internet. So so I circle out the chin and I enlarge that portion. I actually read all the RGB numbers. Those are real numbers from that picture. We can see uh, there are two portions I highlighted, one with the edge, one without the edge. The one circled with the black box has a diagonal edge, means the edge is diagonal. The lower left corner is really bright. It has 111, 112 intensities. On the upper right corner, it's darker, so the intensity is lower, it's 40, 41s. And then by looking at those numbers, we can see, okay, there's a dramatic intensity change from the lower left to the upper right. So there must be an edge in the diagonal direction. Compared to um, compared to the yellow greenish highlighting, there's no edge whatsoever. So it's just simple plain 40s all the way around. So it's just 40s, 41s. It's nothing going on. So that is not an edge. Simple as that. So we can see that as a person we want. Now the goal is to give the computer the ability to see what we are already seeing. So this is basically what this convolution does. Now, when there's an edge, we mentioned the lower left corner, which is the blue highlighting, is 112. It's dramatically different from the upper right corner, which is highlighted in red. Now, if we take the lower left, the blue portion, we, we use that, we add them together, and minus um, the red portion. What we see is when there is an edge, there's a big difference. So when we use the blue portion to minus the red portion, there's a big difference. However, when there's no edge, when all the pixels have similar intensity, we take the blue and red, we uh, use the blue minus the red, the difference is really small. So essentially, if the difference is really big, there's an edge. If D is small, there's no edge. Simple as that. And then basically up until this point, we use our brain. We hand calculated the one convolution computation. Now, why is that convolution? It's simple because remember we mentioned the convolution is we first multiply and then add them all together. Say if I have a matrix written here, have 1 on the lower left corner, which is the blue corner, and -1 on the upper right corner with the red corner. when I multiply this 3 by 3 matrix to the original picture I have, then if I multiply it and then add them together, that's essentially the same computation we just did in the previous slide. And what we did is we find the difference. If the difference big is 215, then that is an edge. If d is 3, there's no edge. Same thing, if we use this kernel on the bottom and do the convolution computation, if the result is big, 215, then there's an edge. If there's small, then there's no edge. Simple as that. And now, what we just did is the convolution for one location. Let me go back real quick to remind you guys. We're only doing the edge detection on the chin area of that animal. That's one location. We want to extract all the features for the entire picture. So how do we do that? We recursively repeatedly use the convolution to find those features. And this is exactly what we do here. On this GIF, you can see we're using a 3 by 3 matrix. Let me go back real quick. A 3 by 3, just like we saw at the bottom black box here. This is the kernel. We're applying it to the original picture. This is the kernel convolutional filter. Well, the kernel is a convolutional filter. If I confuses you, a kernel is a convolution filter. Is that 3 by 3 little thing we put to calculate the difference. So we use that kernel to loop around the picture to find all the features. And the resulting 3 by 3 matrix, which is in white color, is the feature map. What the feature map is just it's just recording all the information of that feature. So if we're detecting edges, the feature map would be the edges map. It will record the location of all the edges of the original picture. And that's basically what a convolution is. And here I put a convolution result of the edge detection. So if I apply that kernel to the image recursively going around the loop, I will be getting this image with highlighted edges. If there's an edge, it's highlighted. If there's no edge, it's just black. Okay, now done with the heavy work. Now we're talking about the neural network. There are actually a lot of math details in the neural network, but I will try to walk you guys through in a higher level. So essentially, what neural network does is it combines all the features. Again, as human, we automatically see a bunch of features, then we combine it in our head in a split second, then we notice it's a dog. And if we were trying to argue with somebody, if that's a dog or a cat, we would say, look, that thing has a curly tail, has paws, and has a pointy triangle ear, and that's a dog, that's not a cat. The reason we're saying that is because we're extracting all the features and we're combining that features into a creator, into an item. And the neural network works the same way. Essentially, after the convolution, the image is represented in a different way. There are no more numbers. Well, essentially, they are all numbers in the computer, but after convolution, there are a whole bunch of features because we extracted a lot of features. Then we need to give the computer the ability to combine the features and basically came out with what it is as an item. So this is the typical easy representation of a fully connected neural network. Say we're using that in our image recognition content, because if we use that in different content like natural language processing or something else, the function will be different, but the network architecture is the same. So, given we are trying to recognize images, uh, we will use this basic structure of the model and to combine all the features. And now this may seem really confusing to you guys. I will try to break it down uh, as further as I can, and it's really not that hard to understand at that point. So first, the input layer. Excuse me. The input layer has three layers. That's red, green, and blue RGB. And then there's first hidden layer, small detail, and the second hidden layer is a local feature, and the third layer is item level feature. I will go through that in a later detail. I will first start with explaining what is a circle in that map. So, what is a circle? The circle is called a neuron, but what it really is just a place to store data. In the context of image recognition, as we mentioned, the image is a three-layer matrix. So one neuron is the place to store those matrices. So essentially, it's just a matrix. If we go back, we have three input. We have three yellow input neurons that represent red, green, and blue matrix. Simple as that. So we put red in the first, green in the second, blue in the third. And what are the lines? Okay, the lines is a neuron connection, um, and what it really is just a path of the data. It starts from the left and at the right. So left is the input, right is the output. And line is not simply passing through data. We're doing computations here. Since we're extracting features, obviously we're trying to use convolution. As we mentioned earlier, in the convolutional part, we want to use convolution to extract all the features throughout the entire picture. Now what we do is we pick one filter, the filter as kernel as the one we mentioned about the 3x3 thing we use to extract the edges. That's a filter. We pick one filter, we do a full convolution of that picture, and we will get a feature map. The feature map is where we store the information of all the features. And one convolution computation for the whole image is the one line in the neural network. What I have here, you can see is the red layer of the original picture. I apply it with the filter. I do a full convolution of the whole image, and I will be getting a feature map. That feature map is the green neuron in the first hidden layer, in the second column of the uh, deep neural network drawings. So essentially, the neuron connection, the lines, are basically a full convolution computation of that image of a specific filter. Now, why are there green circles? Why there are four green circles? Why not four? Why not three? Why not five? Why not 128? So here comes another important concept that I want you guys to know. Remember, we go through the convolution filter or kernel as interchangeable words. So we go over the filters previously in the edge detection part. Um, that filter is only doing one computation, which is take the lower left corner, take the intensity of the lower left corner, and minus the intensity in the upper right corner. And that computation can only find one feature, which is the edge. In that case, so which it means if we have one filter, that filter can only detect one feature. is if we have another feature to detect, if we want to detect more features, we will have to use different filters or different kernels. And this is a really important point because that explains why there are four green neurons in the second and the third and fourth layer because in the neural network we are using four different filters. We are only using four, so we're getting four. As an example here, if we were detecting edge, curve, points, and sharp angle, we apply four different filters to the original image, and we will get four feature map. And each feature map are representing the location, the information of the feature that filter can detect. So in that case, we have four filters, so we end up with four feature map, and we are extracting four features. Now, what I want to point out is this is a really simple representation of a neural network. Typically, we have a lot more than that. Um, Normally, people use 64, 128, and even 256 filters, in which case they are extracting 256 features from one picture. And that's how you know that this is a really powerful method in terms of recognizing picture, because as a human we are not even able to pick up all those features. Okay, and done with so now basically you guys understand what a neural network is. A neuron is a number, a line is convolution, and it just pass all the data layer by layer to the end of the output. Now, here comes the question: how a neural network combine the features? Um, we can think of neural network as as a company. So the first layer neurons are like the low level workers that only working on really simple stuff like collecting numbers, uh, doing all the little work, clean up the table, and then once it's done with the little work, it gives its result to the manager, and the manager look at sales, look at sales work, look at the R&D work, and then the manager do his job and finish his job, and then put his result to the next level, the general manager. And the general manager will look at different, say, tasks and different project and finish with their own project. And then it reports to the CEO, and then the CEO controls the whole company. Um, this is the same story with the deep neural network. Um, the first layer, the very first column here, the edge and line and point, these are really simple basic features. We want the neural networks to be able to see the little features first, and they're only good at searching those little features. They only do one job. Once they do their own job, they pass the information to the next layer. Then the next layer neuron will look at, okay, there's an edge, and there's a line, and there's a triangle, and there's not a triangle. The triangle neuron will identify all the triangles uh, based on the edge and line and point information, and it's only able to detect the triangle, nothing else, nothing more. And then, however, though it's very limited, but it was connected in a third layer. It will pass its information to the triangular ear. Now the triangular ear neuron will look at, okay, there's a triangle and there's a circle, and this triangle looks like an ear, but that triangle doesn't look like an ear. So I will say this is the ear, and this is not an ear. So the triangular neuron really find out the ears based on the previous information provided by the previous layer. And then once we're at the third level, we're already identifying and anatomies, body parts of the animal, and then we feed all those information to the output layer. The output layer will say, okay, it has a ear, it's a furry body, 4 paws, that's a dog. So that's basically how neural networks combines all the features. It works in a layer by layer architecture, each layer and each neuron only working on its specific job and provide information to the next layer. By using this layer by layer architecture, it's only do one thing and it's only doing well in one thing. But because they are focused on different levels, essentially the output will be really accurate. Okay, now we're done with the deep neural network. We will touch on uh, why is it deep learning instead of deep computation. Um, the previous two parts gave the computer the ability to extract features and combine features and basically come up with um, a summary of what the picture is. But um, it is more important. The more important job is we want the computer to be able to learn as we are able to learn. So we will provide a bunch of data with ground truth and letting it know what this picture is. What computer can do then is extract all the features and remember if an image has those features and combined in a certain way, then there's a dog in that picture. There's that thing in that picture. This essentially is a similar learning curve, learning experience as we do as human. So here comes the value of the label. We have to label the picture correctly and clearly, and with really wide variety, so that the computer can learn from what we provide as the knowledge base, the training data. Now, yeah, here's another important idea of how deep neural network works. Uh, Remember we talked about labels. Um, I think one common question when you really think about this thing is, um, it is necessary to provide the labels for all the neurons. Because remember we have 3 by 4, 12 neurons, not 9 neurons. Do we have to manually circle each part, or do we only label the outputs? We only tell the computer that this is a dog, and we let it figure out by itself how to combine edges, triangles, circles, and body part. So if we want to do that, there's a mechanism called backpropagation. The backpropagation means the information um, transform was transported from the end, which is the output, back to the input. If we are given this picture to the computer and let it learn, after the learning, we tell the computer that this is a dog, and then we apply backpropagation. This is a function that built into a lot of the programming languages, so it's really not that hard. Um, so you can ignore the details, just get the bigger picture. What it really is the computer will learn from the knowledge that this is a dog, and it will remember that anything with triangular ear, furry body, and 4 paws is likely to be a dog. And then when it propagates backwards another level to the triangle, circle, and polygon level, it will then automatically say, okay, I have a triangular ear. Now, what do I look for in the triangle and circle combination? If I have something similar to this picture, to this combination, then I know that this is a triangular ear. So from the later the outer layer, from um, from the output layer, we backpropagate once. to let the computer learn a triangular ear. And then we back propagate one more time so that the computer can learn what is a triangular ear. And then we back propagate once more to let this let computer learn what is a triangle, circle, and how what the combination of edge, line, and point makes a proper circle or polygon. So this is how a computer learns by itself. We only provide the final answer, and it will be able to trace all the way back and learn to adjust each tiny neuron. And now the value of the data. Now we know how computer learns. It is really important for us to provide the right knowledge, the correct knowledge, and as well as a variety of knowledge. Say if we're doing a really easy task to differentiate a dog and a cat, I would say a normal average model would be able to do that with like 30 minutes of training or so. It is a really simple task because they're really different from each other. However, if we want the model to be able to differentiate two really similar things, like a fox and a Japanese Shiba, um, that are naturally look alike, then we might need to provide a lot more data and use more complex deep neural networks to let computer extract really detailed information to be able to differentiate those. Also, there's extreme occasions. As a human, we see object and we can combine to our experience. So we know that that dog probably break a couch and have his head out, and maybe and we can also tell the dog smash his face into the glass, and maybe we can also tell the owner of the dog cut his fur to make it look like a line. However, compared to us, the computer doesn't have a lot of real life experience. It doesn't know what is a couch. It only knows what we tell it what it is. It may treat, it may seem like, okay, there's only a head, there's no body, so it's probably not a dog because they're missing four paws and a curly tail. Uh, on the Similarly, on the third picture, if there's two missing ears, the computer will say, okay, there are no ears. It might not be dog. So it is our job to provide some extreme occasion to the computer, so that at least the computer knows when some weird things happens, it's still a dog. It's okay to miss something, but it's still a dog. So that covers why we need to provide a variety of data. And now, how much data should we give the computer to learn? Um, this is not that quite similar to human because we learn really quick. We may be able to see two or three dogs to determine all the dogs. But for a computer, because it works from scratch, it started from really detailed features and numbers. We need to give them a lot of data to be able to learn. A general rule of thumb is at least 100 image per label. And if we want the model to detect multiple class within one image, like I provided here, that model is called YOLO. You only look once. It's a really famous deep neural network model. I believe it can detect up to 50 something labels. So um, it's one of the great examples is there's a video on YouTube. You can search it, the YOLO on autonomous car is able to detect 50 different kind of things on a real time, taking the input from the dash camera. So if you want to build a complex model like that, you will need to expand um, your training data to 200, 300, maybe even more training data per label. And then we also need to cover the variety of data. As I mentioned above earlier, we have to cover those rare occasions, and at the same time, we also need to notice that um, what our potential goal for our model. If it's trying to distinguish a dog, there are a lot of different breeds. They are all dogs. They just look really different. Similarly, if we're trying to identify vehicles, vehicles can be generally really naturally really different. So we have to include all different kinds of vehicles to expand the variety of our training data so that computer knows um, they are all cars. And another example in our project of the roof detection project, to cover the variety of training data, I think it's a good idea to include um, the roof picture in different time of day and in different weather and and in different um, season, because the environment is different, because the different of the environment, it will invoke a lot of the difference in the detail of the picture. And some of them may confuse the model and say, okay, I never seen that, it may not be a roof risk, but in fact it is. So we have to include all kinds of information. And so that's basically it, um, for the value of the data. Essentially, the goal of this presentation is for you guys to understand how image recognition works, and also I want to really indicate the value of human knowledge, because we have to present our knowledge to the computer so that computer can learn. That given our time of the day, given the technology level and the computational power, if we give the computer garbage data, it will not be able to learn anything. So, um, as fancy as this may sound like, um, essentially it all comes down to human work and human experience. We have to transfer our knowledge to the computer, and that all lies on how accurate our training data is and how variety our training data is, and and the pure quantity of our training data. Okay, and that basically summarize my presentation. If you have any questions, you can reach out to Dr. Ming, or reach out to me. I believe Dr. Ming will provide my information. So if you're interested or have any questions, feel free to ask me. And um, I hope this lecture is at least interesting and make you understand more about deep neural network and how image recognition works. And thank you.